Good afternoon and welcome back. Today, we focus on deep convolutional generative adversarial networks, DCGANs, and what they mean for research in computer vision and generative modeling. DCGANs pair convolutional networks with a two-player game, a generator that tries to create convincing images and a discriminator that learns to tell real from synthetic. By training on image data, these models learn hierarchical, spatial representations and can produce new pictures that look strikingly real. In this session, we'll unpack their core ideas, how they're built, and why they've mattered for innovation in AI and vision. Here's the plan for today. We'll start with a quick recap of GANs, the setup where a generator tries to craft fake images while a discriminator spots the real from the fake. Then we zoom in on DCGAN, what makes this deep version special, and how it sits in the broader GAN family. Next, we'll unpack the DCGAN architecture, the essential layout, and the kinds of layers that help the model understand and generate images. We'll cover training DCGANs, how the two networks learn by competing and improving over time. Then we'll look at results and evaluation, how we judge if the generated images look convincing. We'll touch on improvements and variants, and explore some key applications in art, design, and data generation. Finally, challenges and future directions, plus a quick wrap-up and where to read more. Welcome back. So far, we've seen that a GAN is a duel between two neural networks. The generator crafts samples and the discriminator judges them for realism. They push each other to improvements, producing more believable images, sounds, and even text. In the next slides, we'll translate that idea into practical steps and examples. How GANs create fresh pictures, color grayscale photos, or augment data for other models, and why researchers care about ethics and safety as they explore misuse and bias. Then we turn to three big challenges that show up in real projects. First, mode collapse, the tendency to overproduce a narrow set of outputs. Second, training instability, the tug-of-war that can swing learning up and down. Third, evaluation, the lack of universal metrics and the role of subjective judgment. We'll cover intuitive fixes, from balancing training and diverse data to clearer evaluation strategies, and what this means for responsible use. Building on the core duet, this section highlights how researchers stabilize GAN training, quantify progress, and extend the framework with hybrids and specialized objectives. First, stabilization and reliable optimization. In practice, the discriminator's role as a critic needs controlled capacity, so techniques like spectral normalization are widely adopted to bound the Lipschitz constant of the critic. This helps stabilize gradients flowing to the generator. Gradient penalties. As in the Wasserstein GAN with gradient penalty, enforce smoothness of the critic with respect to its inputs, reducing oscillations and mode collapse. Alternative loss formulations, such as the hinge loss, often yield sharper decision boundaries and more stable updates than the original log likelihood objective. Researchers also exploit two timescale learning, where the generator and discriminator are updated with different learning rates and update frequencies to prevent one network from overpowering the other. Taken together, these techniques turn the adversarial game into a more predictable optimization landscape. Second, evaluation and diagnostics. Traditional scores like inception score tell you about confidence and diversity but can be misleading in isolation. The Fresheth inception distance (FID) has become a standard because it compares the real and generated distributions in a deep feature space, capturing both quality and diversity more robustly. Kernel inception distance (KB) provides a bias-corrected alternative. Perceptual metrics such as LPIPS measure visual similarity in a human-aligned feature space. Practically, researchers report a small suite of metrics, FIT, KID, LPIPS, and sometimes precision recall curves for realism and coverage, to avoid over-interpreting a single score. Always couple metrics with qualitative inspection and, when possible, domain-specific validity checks to guard against biases in the data. Third, hybrids and extension that broaden applicability. Conditional GANs enable control by labels essential for targeted synthesis. Hybrid architectures like VAE GANs fuse probabilistic latent modeling with adversarial refinement to improve sample quality while preserving latent structure. Self-attention mechanisms, as in SAGAN, capture long-range dependencies crucial for high-resolution imagery. Style and progressively grown GANs A. G. ProGAN divided by StyleGAN improve realism and control over appearance. You can also combine GANs with other generative paradigms, flow-based models, diffusion models, or variational components to leverage complementary strengths. In many domains, paired with domain knowledge, such hybrids become practical tools for data augmentation, simulation, or image-to-image translation. Finally, a note on responsibility. As GANs become more capable, ethics and safety detection of fakes, awareness of biases, and clear communication about synthetic origins remain essential. With careful evaluation, robust training practices, and thoughtful deployment, GANs offer a principled, high-impact toolkit for research and application. Building on the challenges you see with traditional GANs, I'd like to expand the conversation beyond the basics and connect them to practical, advanced strategies researchers now employ to push reliability and realism. First, mode collapse. We know it narrows the generator's output to a limited set of patterns, harming diversity. Beyond broad data augmentation and conditional generation, several targeted techniques have become standard. Mini-batch discrimination and related statistics encourage the discriminator to look for diversity across a batch, discouraging the generator from repeating the same modes. Unrolled GANs provide the generator with a longer-term view of the discriminator's updates, reducing premature convergence to a subset of modes. On the regularization side, spectral normalization constrains the Lipschitz constant of the discriminator via an eigenvalue estimate, often with power iteration, helping the feedback signal to remain informative without explosive gradients. Gradient penalties, as in WGAN-GP, explicitly enforce a one Lipschitz constraint along interpolated samples, stabilizing updates and preserving gradient flow. These tools, together with tailored latent spaces and mode-seeking losses, help preserve a richer, multimodal distribution rather than collapsing to a few patterns. For evaluation, we increasingly pair automated metrics with qualitative checks to detect hidden collapses. A familiar visual cue can be complemented by quantitative diversity measures. Second, training instability. The adversarial tug-of-war can produce oscillations and stalls. To tame this, researchers deploy two timescale update rules, different learning rates and update frequencies for the generator and discriminator to prevent one side from outrunning the other. Gradient penalties and spectral normalization again play a central role by enforcing smoother gradient landscapes and stable updates. Architectural choices such as conditioning, skip connections, and careful normalization also contribute to steadier learning. Regularization strategies like instance noise or data augmentation further damp high-frequency oscillations. When instability is stubborn, hybrid approaches can help, combining an autoencoder backbone via GAN style to stabilize the latent space, or integrating diffusion-like refinement stages that progressively sharpen samples while keeping the GAN's fast sampling speed. The result is a more predictable convergence behavior and less sensitivity to hyperparameter sweeps. Third, evaluation remains non-trivial. FID and kernel inception distance are the workhorses, yet they don't capture everything blindly. Chasing a lower FID can miss mode coverage or perceptual flaws. Complement FID with precision recall analysis for GANs to diagnose diversity versus quality. LPAPS-based perceptual metrics for fidelity and task-relevant proxies such as downstream classifier accuracy on synthetic data. Some teams advocate hybrid evaluation, automated metrics plus structured human judgments, and even task-based assessments, AAG. How well-generated images augment downstream models. As with mode collapse and instability, no single score suffices. A suite of metrics with transparent reporting becomes essential. Next, we zoom into DCGANs, a powerful blend of two networks that play a game. A generator tries to turn noise into believable pictures, while a discriminator learns to tell real from fake. We'll break down why replacing fully connected layers with convolutional ones matters, locality, scale, and preserving spatial structure, why DCGAN skip pooling and keep the image texture intact through careful strides and extra convolutions. We'll explain batch normalization and how it stabilizes training, so the models learn faster and produce sharper images. You'll see how these models generate convincing faces, landscapes, and textures, and why this matters for art, design, and data augmentation. We'll also touch on the design choices that avoid common pitfalls and raise important questions about ethics when synthetic images become easy to produce. Building on the DCGAN lineage, researchers quickly moved beyond the vanilla recipe to tackle stability and realism head on. In contemporary practice, you'll often see two strands of refinement working in concert: regularizing the critic with normalization and objective penalties, and evaluating generative performance with metrics that align more closely with human perception. First, spectral normalization. This technique regularizes each weight matrix by its largest singular value, effectively constraining how much a layer can amplify input signals. The consequence is more predictable gradients and a smoother optimization path as you stack many convolutional layers. In practice, this helps prevent runaway updates in the discriminator, which in turn makes the generator's task less volatile and more tractable across training runs. Second, gradient penalties, exemplified by the WGAN GP paradigm. Rather than only shaping the loss landscape through scores, the gradient penalty enforces a constraint on the gradients of the critic with respect to its inputs, encouraging their norms to hover near 1 along real-fake interpolations. This reduces mode collapse, lowers sensitivity to initialization, and yields more faithful distributional coverage of the data. Modern DCGAN-inspired models often combine a spectrally normalized discriminator with a gradient penalty, striking a robust balance between realism and diversity. Evaluation metrics have evolved alongside these advances. The freshest inception distance, or FID, compares real and generated samples in a pre-trained feature space to quantify both similarity and diversity. Lower FID indicates closer alignment with the real data distribution. The inception score remains informative but has known caveats, particularly around diversity versus quality trade-offs. So best practice is to report multiple metrics and, where feasible, precision recall diagnostics for generative models. Careful experimental design, consistent pre-processing, multiple seeds, and transparency about dataset characteristics is essential to avoid overinterpreting a single score. Hybrid and conditional variants broaden what DCGANs can do in practice. Conditional DCGANs inject label information to enable class condition synthesis. VAE-GAN hybrids merge probabilistic encodings with adversarial sharpening to improve likelihood estimates while preserving sharp images. And the lineage has influenced later systems like StyleGAN, which retain adversarial training while offering deeper control over style and texture. Taken together, these developments illustrate a shift from a fixed recipe to a modular toolkit. Stability, availability, and controllability become central design criteria. In short, DCGANs open the door to imaginative synthesis. But the contemporary toolkit, spectral normalization, gradient penalties, robust evaluation, and thoughtful hybrids lets researchers push toward higher fidelity and more reliable, interpretable generation in real-world settings. Building on the core DCGAN design, we can push stability and realism even further by integrating a few well-mastered techniques that have become standard in modern GAN practice. Today, I'll sketch how these ideas fit with the DCGAN philosophy: convolutional, stride-based downsampling, and a fully convolutional generator and discriminator without abandoning the advantages of preserving spatial structure. First, consider spectral normalization. By constraining the spectral norm of each layer's weight matrix, the discriminator, and to a lesser extent, the generator, gains a more predictable Lipschitz-bounded behavior. In practice, this keeps the discriminator from exploding in its gradients as the network grows deeper or trains on larger images. The result is a smoother optimization landscape, more stable alternating updates, and empirically sharper, more diverse outputs when you stack several convolutional stages, the same architectural spirit as DCGAN, but with a principled regularization baked in. Second, gradient penalties offer another route to stability. The WGAN GP paradigm adds a penalty on the gradient norm of the discriminator with respect to its inputs, encouraging one Lipschitz behavior in a data-driven way. This tends to reduce mode collapse and helps the generator explore a broader portion of the data manifold. When incorporated with the DCGAN style architecture, you can retain the clean feature hierarchy of convolutions while enjoying steadier gradients and more reliable convergence even as you push toward higher resolution outputs. Third, moving beyond a single global discriminator to robust evaluation and feedback is crucial. In practice, you can adopt multi-scale or patch-can inspired discriminators that judge realism at multiple resolutions. That aligns well with DCGAN's emphasis on spatial coherence. Texture and structure are validated at coarse, intermediate, and fine scales, encouraging the generator to maintain consistency as images scale up. Fourth, evaluation has evolved beyond visual inspection. Fresheth inception distance and kernel inception distance K offer quantitative gauges of realism and diversity by comparing statistics of generated and real images in feature space. When you report FID alongside traditional qualitative checks, you obtain a clearer sense of both image fidelity and coverage of modes. Pair these with precision recall GAN metrics to separate perceptual quality from diversity. Finally, hybrid models remind us that DCGAN's idea, strong convolutional priors without pooling, plays well with rich latent and reconstruction objectives. Variants like VAE GAN hybrids or encoder-decoder variants can provide meaningful latent representations for inspection and downstream tasks while still leveraging the adversarial objective to sharpen details. In short, DCGAN's architectural clarity, no pooling, stride-based convolutions, and persistent spatial structure serves as a solid foundation. Layering spectral normalization, gradient penalties, multi-scale feedback, and principled evaluation turns that foundation into a scalable, modern framework for high-fidelity, diverse synthetic imagery. Up next, we pull back the curtain on the DCGAN duo, the generator and the discriminator, and watch how they learn to play off each other. The generator starts from a random seed and, through upsampling with transposed convolutions, grows a picture step by step. Convolutional layers, refine edges and textures. ReLU keeps learning brisk, and TANH scales the final pixels. Batch normalization helps training stay steady and later adds variety. The discriminator, meanwhile, acts as a keen judge using stacked convolutions, leaky ReLU to stay alive, and strided convolutions in place of pooling to preserve detail as it downscales. Then we'll summarize 3 practical design rules. Drop fully connected layers to retain layout and speed, replace pooling with learned downsampling, and enforce architectural constraints to prevent mode collapse. Together, these ideas shape sharper images, safer content, and richer creativity. Building on the practical recipe for the DCGAN generator, there are several advanced levers researchers routinely pull to improve image quality and training stability without changing the core idea of mapping a seed to a complete image. First, consider stability constraints on the networks themselves. Spectral normalization is a powerful tool that constrains the Lipschitz constant of the discriminator and, in some setups, the generator. By stabilizing how quickly the discriminator can react to small input changes, spectral normalization reduces oscillations and helps the generator learn smoother, more meaningful mappings. Relatedly, gradient penalties, most notably in WGAN-GP, replace the standard adversarial loss with a penalty that enforces Lipschitz continuity by constraining gradients. This often yields more stable convergence and better coverage of the data manifold, mitigating mode collapse tendencies without excessive hyperparameter tuning. Evaluation becomes more than a qualitative check. The Frechet inception distance has become a standard benchmark. It compares the statistics of real and generated images in a high-level feature space, typically from an inception network. Lower FID indicates closer distributional alignment, including both fidelity and diversity. When using FID, be mindful of sample sizes and dataset biases. Complementary metrics such as the kernel inception distance, KID, or precision divided by recall for generative models can provide additional insight into diversity versus quality and help reveal mode leakage. On the architectural side, several refinements are common in modern generators. Style-based generators, StyleGAN, and successors introduce a mapping network that converts the latent code into a per-layer style vector, enabling fine-grained control over synthesis at different resolutions. This is often paired with adaptive instance normalization to inject style into early and late layers, supporting impressive variety and realism. Hybrid models such as VAE GANs or conditional GANs with projection discriminators combine complementary strengths, probabilistic latent modeling or explicit conditioning to guide outputs toward known attributes or labels. There is also a practical concern with transposed convolutions, checkerboard artifacts. Many practitioners mitigate this by upsampling with nearest neighbor or bilinear methods before a regular convolution, or by using anti-alias down divided by upsampling schemes and careful stride choices. Batch normalization is another design choice worth reconsidering, with small batches or certain objectives. Alternatives such as instance normalization, layer normalization, or even avoiding BN in the generator can stabilize training and improve sample consistency. Let's extend the picture of how the discriminator operates in a DCGAN by looking at some enhancements that researchers now routinely consider to improve stability, texture, fidelity, and evaluability. The core idea remains: the discriminator learns hierarchical features that separate real from fake. But several advanced techniques push this further. First, spectral normalization. By constraining the spectral norm, the largest singular value of each weight matrix in the discriminator, we keep its Lipschitz constant in check. This prevents the discriminator from becoming overly strong relative to the generator, which can destabilize training and induce poor gradient signals. In practice, you attach a spectral normalization operation to convolutional layers so that the discriminator's responses remain well behaved across updates, promoting smoother gradient flow back to the generator. Second, gradient penalties. Inspired by Wasserstein GANs, gradient penalties encourage the discriminator to have gradients of unit norm on interpolated samples between real and fake. This enforces a more stable, continuous shaping of the decision boundary and mitigates common GAN pathologies like mode collapse and oscillations. In a DCGAN setting, you can adopt a gradient penalty term as an auxiliary objective alongside the standard adversarial loss, improving convergence in challenging datasets. Third, architectural variants that sharpen texture and detail. Patch GAN discriminators evaluate the realism of small image patches rather than the whole image at once. This local focus forces high-frequency details, textures, grain, edge, sharpness to be globally coherent when stitched together. A complementary approach is to use multi-scale or multi-branch discriminators. One branch attends to fine-scale patches, another to coarser global structure. This combination helps capture both local textures and overall composition. Fourth, attention mechanisms. Incorporating self-attention or non-local blocks allows the discriminator to model long-range dependencies, which is especially beneficial for faces, landscapes, or scenes where distant regions influence each other. Attention can help the model distinguish, for example, realistic shading and spatial relationships that simple constructs might miss. Fifth, evaluation and training signals. Beyond the standard adversarial loss, practitioners use feature matching losses, minimizing differences between real and fake features from intermediate layers to stabilize training and promote diversity. For evaluation, Frechet inception distance and, to a lesser extent, inception score IS provide quantitative gauges of realism and diversity, guiding architectural choices and hyperparameters. However, they should be complemented with human judgment and task-specific metrics. Finally, the idea of hybrid models. DCGANs can be combined with variational or perceptual objectives e.g. VAE GAN, perceptual losses, to leverage complementary strengths, robust latent structure, richer global coherence, and sharper textures. These choices, spectral normalization, gradient penalties, patch divided by multi-scale discriminators, attention, and hybrid losses, shape what the discriminator learns and, in turn, what the generator can reliably synthesize. The result is more convincing AI-generated visuals with clearer textures, better global consistency, and more trustworthy outputs for games, art, and research. Thank you. Building on the 3 design principles you see summarized here, researchers have pushed DCGANs toward more stable learning, sharper images, and better coverage of the data distribution. I'll expand each principle with what has become standard practice in the field, including stabilization techniques and robust evaluation. First principle, removing fully connected layers. The canonical DCGAN generator and discriminator rely on convolutional layers throughout, which helps preserve spatial structure and keeps parameters in check. Beyond this architectural choice, we now routinely bolster stability with Lipschitz preserving mechanisms and regularization. Spectral normalization, applied to the weights of each convolutional layer, constrains the spectral norm and yields more predictable gradient flow, reducing extreme updates that can chaos the training. When paired with gradient penalties, most commonly the WGAN GP penalty applied to the discriminator's loss, we enforce a soft Lipschitz constraint that encourages smoother decision boundaries. These additions complement the FC-free design by promoting stable convergence, even as we push for higher resolution outputs. In tandem, evaluation with metrics like the Frechet inception distance provides a quantitative lens on realism and diversity, helping us judge whether removing dense connections translates into perceptually better images and a fuller coverage of the target distribution. Second principle, strided convolutions instead of pooling is less than #0. 5 hash is greater than strided convolutions learn where to downsample as part of optimization, preserving useful features while reducing resolution. This learned downsampling tends to yield sharper, more coherent textures than fixed pooling. However, it introduces considerations about artifacts such as potential checkerboard patterns from certain upsampling divided by deconvolution schemes. Contemporary practice often mitigates this by combining strided downsampling with careful architectural choices A, G, anti-aliasing in downsampling, or using upsampling followed by convolution to control artifacts. In practice, the benefits extend beyond feature quality, smoother gradient flow, and more stable training when the discriminator and generator co-evolve under a learned scale of representation. When we measure progress, FID and related metrics again guide whether the downsampling choice improves both quality and diversity of generated samples. Third principle, architectural constraints. Beyond normalization, modern DCGAN-inspired systems incorporate auxiliary constraints designed to curb mode collapse and encourage variety. Spectral normalization on the discriminator is a prime example, but so are gradient penalties and carefully chosen loss formulations A, G, hinge, or Wasserstein-based objectives. These constraints help the two networks learn together more harmoniously. Additionally, researchers explore hybrid models that blend DCGAN-style architectures with ideas from VAEs, conditional extensions, to leverage labels, or progressive growing strategies to stabilize high-resolution generation. Across these efforts, robust evaluation with FID and where appropriate IS remains crucial to balance image quality and distributional coverage. Next, we pivot from the big picture to the data that makes DCGANs work. We'll peek at how datasets are prepared and why CelebA and CIFAR 10 are popular choices for practice. You'll hear about resizing and scaling images to the -1:1 range, plus why shuffling and normalization matter for stable training. We'll outline the pre-processing steps that keep batches consistent and help the model converge more reliably. Then, we turn to data augmentation, small, deliberate changes that broaden the generator's experience, including rotations, flips, and color tweaks. We'll note that 14 common techniques cover a wide range of visual variation, with the order of application sometimes shaping robustness. Finally, we'll connect these choices to the realism we aim for and how they influence training dynamics as we move into adversarial loss and the practical training setup in the upcoming sections. Let's zoom into dataset preparation for DCGANs with an eye toward robustness and reproducibility. Two datasets commonly used in this space are CelebA and CIFAR 10. CelebA provides a large, diverse collection of celebrity face images with a range of expressions, lighting, and poses, which helps the generator learn realistic facial textures and variability. CIFAR 10 supplies 10 object categories with varied textures and shapes, encouraging the model to learn general-purpose features that transfer beyond faces. Together, they offer a broad coverage of visual concepts, which helps the generator reason about faces in different contexts and about objects in different contexts. From a pre-processing perspective, the standard recipe is to resize images to a fixed resolution and scale pixel values to the range -1, 1, aligning with the tanh output used in many DCGAN implementations. Shuffling the dataset before each epoch is essential to prevent order-induced biases and to promote stable gradient flow. In terms of network regularization, batch normalization has been a staple in DCGANs to improve convergence and gradient flow across layers. It also helps the generator learn consistent texture and structural cues across batches. However, be mindful of its interaction with the discriminator. Modern stability practices often trade or supplement batch normalization with spectral normalization or gradient penalties to enforce Lipschitz constraints and mitigate mode collapse, especially when pushing toward higher fidelity or more stable training across diverse datasets. Data augmentation is a powerful lever in practice. It increases sample variability, reduces overfitting, and helps the model generalize to unseen conditions. The classic augmentations rotation, horizontal flipping, and small scaling are common, but a broader set of 14 techniques is often employed, including color, jitter, brightness, divided by contrast adjustments, cropping, and minor geometric distortions. The key is to apply augmentations on the fly during training while preserving the semantic integrity of the images. The order and combination of augmentations matter. Some sequences yield more robust models by simulating realistic camera variations without introducing unrealistic artifacts. Evaluation plays a crucial role in guiding these choices. Freshet inception distance. is now a standard metric for gauging both realism and diversity of generated images, especially when working with faces and objects across multiple categories. It's informative to report feed alongside qualitative samples. Complementary metrics such as inception score, MSSIM for diversity, and precision recall analysis provide a fuller picture of both quality and coverage. When comparing setups, it's helpful to vary augmentation regimes, normalization strategies, BN versus SN or penalties, and loss formulations, then track FID trends and sample realism. In short, effective DCGAN data preparation blends diverse, well preprocessed sources with disciplined normalization, principled augmentation, and rigorous multimetric evaluation. This foundation often translates into more stable training, faster convergence, and higher quality, more realistic outputs across varied domains. Adversarial loss remains the organizing principle of DCGAN training, but in practice, we tune and augment it to keep the game stable and interpretable. Beyond the simple tug of war, researchers apply architectural and optimization safeguards that regulate the discriminator's capacity and the gradient flow, so the generator can catch up without being overwhelmed. One key refinement is spectral normalization in the discriminator. By constraining each layer's spectral norm, we keep the discriminator from jumping to extreme gradients, effectively policing the Lipschitz constant and smoothing the loss landscape the generator sees. This tends to reduce spikes in updates and improves reproducibility across runs. Relatedly, gradient penalties, most famously in the WGAN GP family, impose an explicit penalty on gradient norm violations. Rather than clipping weights, these penalties encourage the discriminator to behave like a one Lipschitz function, yielding more meaningful, monotonic improvements in generator quality and often more stable convergence. Evaluation beyond the adversarial loss itself is essential. Freshet inception distance has become a standard. It measures how close the generator distribution is to the real distribution in a learned feature space, balancing realism with diversity. In practice, you track FID and to a lesser extent inception score over epochs to gauge progress rather than relying solely on the adversarial loss. It's common to report a short-term FID trend during preliminary runs and a longer-term trend as you scale data and training time. Complementary metrics like KID or precision recall curves for GANs can provide additional insight into mode coverage and sample quality. Hybrid and auxiliary objectives are another powerful avenue. Perceptual or feature modality losses drawn from pre-trained networks can guide the generator towards semantically coherent detail while the GAN loss handles realism. Infogan style information regularization or auxiliary classifiers, ACGAN, can promote disentanglement or controllable attributes. In progressive or multi-scale DCGAN variants, auxiliary losses align details at different resolutions, stabilizing training across stages. From a practical standpoint, balance remains key. The learning rate and update cadence must be tuned in concert with these regularizers. Too aggressive a step can destabilize both networks. Too conservative a step slows progress. Longer training with careful monitoring using FID alongside visual inspection often yields the most reliable convergence. And while small, rapid experiments A, G, 1530 epochs are useful for ablations, most robust results come from larger scale runs, tens to hundreds of epochs with thoughtful stabilization. In short, adversarial loss is essential, but modern DCGAN practice increasingly pairs it with normalization, gradient penalties, robust evaluation, and hybrid objectives to push toward realistic, diverse, and scientifically usable image synthesis. Stabilizing DCGAN training is a multi-knob problem, and today we can push beyond the basics by integrating more mature regularization and evaluation strategies. In practice, the stability you observe comes from how the discriminator and generator trade gradients, how we constrain their capacity, and how we measure progress. Let me outline a compact actionable toolkit that builds on batch normalization and the intuitive tricks we discussed, and add 3 advanced levers: spectral normalization, gradient penalties, and rigorous evaluation. First, a spectral normalization. By constraining the spectral norm of each weight matrix in the discriminator, we cap the Lipschitz constant of the network. This tends to produce more predictable gradients and prevents the discriminator from becoming arbitrarily sharp, which in turn makes the generator's learning signal more manageable. In DCGAN workflows, applying spectral normalization to all convolution layers in the discriminator and selectively to the generator if needed often yields smoother convergence curves and reduces mode hopping artifacts. The key is to monitor gradient norms and avoid over-regularization that dampens legitimate signal. Start with the standard SNDCGAN templates and adjust only if you see persistent instability. Second, gradient penalties. Techniques such as WGAN GP or R1 divided by R2 penalties impose explicit constraints on the gradient magnitude, improving the stability of the training dynamics when GAN losses alone are insufficient. A gradient penalty adds a term to the discriminator loss that discourages large gradients with respect to inputs or real data, effectively promoting a smoother loss landscape and better generalization to unseen samples. In practice, couple gradient penalties with spectral normalization for complementary effects. SN controls the weight spectra, while the penalty constrains the local geometry of the discriminator's decision boundary. Expect some computational overhead, but the payoff is typically steadier convergence, fewer sudden jumps in FID scores, and more reliable diversity. Third, robust evaluation and hybrid objectives. Move beyond the instability of single-point metrics by tracking Frechet inception distance or kernel-based distances k'd over checkpoints, not just final performance. FID correlates better with human judgments of realism and diversity, but requires careful interpretation. Fix the inception model, maintain consistent resolutions, and report confidence intervals. Consider hybrid objectives for challenging domains, combining projection discriminators for conditioning, feature matching to stabilize multimodal outputs, or unrolled epochs to mitigate mode collapse. Additionally, two timescale update rules using slightly different learning rates for the generator and discriminator often harmonize their training dynamics when paired with spectral normalization or penalties. Practical takeaway: start with spectral normalization in the discriminator, add a moderate gradient penalty if instability persists, and implement systematic metric-driven evaluation FID divided by KID across staged checkpoints. Maintain a disciplined experimental notebook, run ablations, and tune TTUR settings per dataset. With this integrated approach, you can achieve more robust, reproducible DCGAN training and clearer progress signals in real projects. Next, we'll zoom in on what makes DCGAN stick and how we measure their success. We'll compare the two-player setup, the generator forging images and the discriminator judging realism, and watch how deeper networks push from edges to textures to coherent scenes. We'll contrast that with vanilla GANs, which tend to blur or produce awkward artifacts. Then we turn to the numbers: inception score and Frechet inception distance, what they capture, what they miss, and why we often use both alongside human judgments. We'll discuss persistent challenges, checkerboard upsampling artifacts, color shifts, mode dropping and mode collapse, and training instability. We'll finish with practical strategies to improve realism, data, architecture tweaks, alternative models, and the ongoing balance between realism and diversity. Finally, keep an eye on authenticity and biases as you interpret outputs and think about how these results translate to real applications. Thank you. Building on the core idea of a creator and a critic, we can push beyond the simple dichotomy to discuss how modern refinements shape both stability and quality in DCGAN-like architectures. Even with deep convolutional stacks driving sharper details, training dynamics remain sensitive to how the discriminator constrains the generator. Advanced regularization and normalization techniques give us better control over learning signals without sacrificing expressiveness. First, consider spectral normalization in the discriminator. By constraining the Lipschitz constant of each layer, spectral normalization dampens runaway gradients and helps the generator explore more meaningful directions in image space. This often reduces fragile oscillations and accelerates convergence to higher quality minima. Complementing this, gradient penalties, most notably in Wasserstein GAN variants, enforce smooth, well-behaved gradients that discourage abrupt changes in the discriminator's output. While classic DC GANs benefit from stabilized training, these penalties can further improve stability, especially as you scale to higher resolutions or more complex textures. Second, move from purely adversarial loss to hybrid objectives. Perceptual or feature-based losses, computed from pre-trained networks, encourage outputs to match high-level representations in addition to pixel-level realism. This helps maintain coherent textures and shapes, reducing artifacts that purely adversarial losses sometimes miss. Variational ideas, as in VAE-GAN hybrids, can encourage a smoother latent space and better coverage of modes, addressing issues of blurriness or repeating patterns while preserving realism. Evaluation should accompany generation. In practice, researchers use free-shed inception distance (FID) and less commonly inception score (IS) to quantify realism and diversity. Precision recall analyses offer a lens on mode coverage versus fidelity, helping diagnose whether a model is producing varied plausible images or collapsing to a narrow subset. It's crucial to pair these metrics with human judgment because automated scores may overlook context, texture, subtleties, or domain-specific artifacts. Hybrid architectures also enable richer representations. Conditional DCGANs enable control over attributes, ACGANs encourage disentangled, interpretable features, and VAEs or autoencoder backbones can provide robust encodings that stabilize generation. In practice, hybrids like VAE GANs or style-inflected variants blend the strengths of reconstruction, latent space, structure, and adversarial realism. Real-world uses remain compelling. Synthetic data for games, design prototyping, and research where data are scarce or sensitive. Yet we must continually question authenticity and bias. Some outputs will still surprise with strange eyes or repeating motifs. These artifacts remind us that training, evaluation, and critical scrutiny must go hand in hand. Always test across many samples, compare with real photographs, and interpret metrics in light of the domain. DCGANs, especially when augmented with spectral normalization, gradient penalties, and thoughtful hybrids, illustrate both the potential and the limits of plausible synthesis. Let's build on IS and FID by looking under the hood and thinking about what these scores really tell us and what they can miss in practice. First, IS. The inception score uses a pre-trained classifier to judge generated images. If the classifier tends to assign high confidence labels to many images, IES clients. That sounds straightforward. Clear ideas, diverse labels, a sign of quality. But there are subtleties. A high IES can arise from the generator producing very confident but semantically trivial images, or from artifacts that the classifier consistently misinterprets as distinct classes. Because IES depends on the classifier's priors, it can be gamed by exploiting biases in the model's feature space rather than improving perceptual realism. In short, IS rewards sharpness and label diversity, but not necessarily true perceptual fidelity or meaningful variety from a human eye. Now, FID. The Frechet inception distance compares real and generated images through the features used by the same classifier. It measures the distance between two feature distributions. The closer the fake distribution is to the real, the lower the FID. The strength of FID is that it couples realism with diversity in a single number, and it tends to be more sensitive to mode coverage than older metrics. Yet it isn't perfect. It relies on inception features trained on ImageNet, so for domains outside the distribution, it can misrepresent quality. It also assumes a Gaussian model of the feature distributions, which can be a crude approximation for complex data. Unlike IES, FID can be swayed by dataset biases, sample size, or architectural quirks of the classifier. Advanced ideas you'll encounter in the literature include both training side and evaluation side refinements. On the training front, spectral normalization and gradient penalties, for example WGAN GP, help enforce Lipschitz constraints and stabilize training, which often yields more reliable downstream metrics. When the discriminator learns a more stable decision boundary, the generator tends to produce samples whose distributions align more faithfully with real data, improving both perceptual quality and sample diversity. On the evaluation front, researchers are extending beyond IS and FID. Consider precision and recall for GANs to separately quantify quality, precision, and coverage recall. Kernel Inception Distance Kit provides an unbiased estimator, while LPAPS and MSSSIM offer perceptual and structural similarity insights. Human studies remain vital for ground truth judgments, especially in niche domains. Hybrid models combining GANs with VAEs or diffusion components offer new frontiers. They can capture both sharp textures and richer latent structure, but they also demand careful, multimodal evaluation to ensure improvements are genuine across metrics, not just on a single score. In practice, use a constellation of metrics, monitor human judgments where possible, And remember that numbers translate to perceptual reality only when interpreted in context. Thank you. Let's drill into the practical consequences you see in DCGAN generated images and, crucially, how we move from artifact-prone outputs to reliable, diverse generations. The slide highlights three broad families of issues: upsampling artifacts, training instability, and generalization limits, and each points to concrete architectural and training choices we can deploy. First, upsampling artifacts. The checkerboard patterns and color distortions largely trace back to the way we enlarge feature maps, especially with transposed convolutions. Uneven overlap across pixels can imprint checkerboard textures, and color channels can drift unevenly as signals propagate through layers, producing strange hue shifts. Practical mitigations include rethinking, upsampling, use simple, artifact-free, upsampling nearest neighbor or bilinear, followed by a regular convolution, or employ subpixel, pixel shuffle, or resize convolution strategies. Tuning kernel sizes and stride parity helps as well. Beyond upsampling, stabilizing the discriminator with spectral normalization can prevent the kind of feedback that amplifies these artifacts. Also, modern architectures such as StyleGAN-inspired blocks or progressive growing techniques offer smoother, more controllable detail as resolution increases. Second, training instability and the twin pathologies of mode dropping and mode collapse. When the generator drifts or the discriminator becomes too strong, the model can fail to cover the data distribution, selectively producing a narrow set of outputs. Here, penalties and normalization techniques play a central role. Gradient penalty regularizations, for example WGAN GP, encourage a Lipschitz constraint and smooth the lost landscape, reducing sudden shifts in generated patterns across runs. Spectral normalization in the discriminator further constrains its capacity, helping the generator learn more stable mappings. The well-known 2 timescale update rule, different learning rates for generator and discriminator, also improves convergence and reduces cyclical behavior that invites mode collapse. Third, generalization and fidelity across categories. A DCGAN may generalize well to broad classes but struggle with highly detailed textures like fur or with rare modes in the data. Address this with richer supervision signals and evaluation feedback. Use perceptual or contextual losses to preserve high-frequency details and consider hybrid or hybrid training regimes, GANs with VAEs or encoders or style-based generators to better separate content from style and to promote diversity without sacrificing realism. Hybrid approaches often yield more stable training and better coverage of modes. Finally, robust evaluation is essential. Move beyond visual inspection to quantitative metrics, freshet inception distance to gauge realism and diversity. Inception score with caveats and precision divided by recall for distributional coverage. Complement with perceptual similarity metrics A, G, and diversity measures like MS, SSIM. Together, these guide architectural choices and hyperparameters. Next, we'll outline 3 architectural tweaks that help GANs craft sharper images. First, progressive growing starts with tiny pictures and adds detail gradually, keeping training stable. Second, self-attention lets the model compare distant parts of a scene, preserving layout in busy shots. Third, residual connections provide shortcuts that keep learning steady as networks deepen, reusing useful features. Then we sharpen the training routine. We'll cover Wasserstein laws for smoother gradients, spectral normalization to keep the discriminator from overreacting, and TTUR, which adjusts the learning speeds of generator and discriminator to avoid stalls. After that, we'll see how conditioning, style control, and cycle consistency open new ways to guide and refine generation, even without paired data. By the end, you'll see how these tools fit together to move drafts toward reliable, high-quality images you can use in projects. 3 architectural enhancements help GANs generate better images for learning from real photos. Beyond the intuitive tug-of-war between generator and discriminator, these techniques address stability, capacity, and global coherence in ways that pay off as you scale from simple to complex data. I'll expand each with deeper mechanisms and practical signals you can use in research. First, progressive growing of GANs. The idea is to start training with very low resolution images and a small network, then gradually add layers to increase detail. This staged growth stabilizes optimization by keeping gradient magnitudes manageable and by guiding the model to learn core structure before fine texture. In practice, you'll often fade in new layers to avoid sudden shifts in distribution, and you can couple this with careful normalization and regularization. At the research level, consider augmenting progressive growth with spectral normalization on both generator and discriminator to constrain the Lipschitz constant as capacity expands, and with gradient penalties such as WGAN GP to encourage smooth, meaningful gradients across scales. When reporting results, track FID and, where feasible, complementary metrics like PRD or precision divided by recall for generative models to separate fidelity from diversity. This combination typically yields more reliable convergence and sharper, more stable, high-resolution samples than naive end-to-end training. Second, self-attention GANs. Self-attention enables the model to relate distant regions, enforcing coherent layout in cluttered scenes and enabling long-range dependencies. For example, matching a distant building's edge with foreground elements. The mechanism introduces non-local blocks that compute relationships across spatial positions, often in a multi-head fashion. This improves global consistency, texture uniformity, and the fidelity of large-scale structure. However, attention adds compute and memory overhead, so practitioners commonly deploy it at selected scales, mid to high resolutions, or use relaxed attention, low-rank approximations to keep training tractable. In research, pair self-attention with careful regularization, spectral normalization, optional gradient penalties, and evaluate its impact with FID and human-rated perceptual quality across scenes of varying complexity. Hybrid approaches, combining attention with style-based modulation in the generator, for example, have shown notable gains in detail and coherence. Third, residual connections in GANs. Residual skip pathways facilitate gradient flow and allow deeper networks to reuse already learned features, reducing training instability and enabling more expressive generators and discriminators. Residual blocks help transfer information across layers, mitigating vanishing gradients and supporting reuse of early features for new tasks. They pair naturally with normalization and spectral constraints, preserving stability as depth grows. In practice, you'll want to test residual alongside attention and progressive growth to understand their complementary rather than competing effects on stability and detail. As you design experiments, keep two metrics in view: stability during training and the level of detail in outputs. Use progressive growth as your backbone, add self-attention where scene structure demands it, and incorporate residuals to enable depth. Consider hybrid models that blend GANs with VAEs or style-based generators to exploit structured latent spaces. Start simple, monitor FID and related metrics, and perform targeted ablations to isolate each component's contribution. These techniques, carefully combined, offer a robust path toward high-quality, learnable images for real photo ecosystems. As we move beyond the basics, this slide highlights three interlocking stability mechanisms and then points toward practical extensions researchers use to push DCGANs from good to robust in real-world settings. First, the Wasserstein loss. In practice, this approach does more than softening gradients. It reframes the learning signal as a meaningful distance between distributions rather than a brittle probability ratio. The critic estimates the Wasserstein distance, guiding the generator with gradient signals that reflect actual distributional gaps. In modern practice, this neighborhood-aware signal is often paired with a Lipschitz constraint to prevent explosive updates. You'll see gradient penalties introduced to enforce this constraint more softly and consistently than weight clipping ever did, reducing sensitivity to architecture, choice, and data quirks. The net effect is a smoother optimization landscape that mitigates mode collapse not merely as a heuristic but as a consequence of reliable, lower variance updates over many steps. This translates into more stable convergence and a broader exploration of the data manifold. Second, spectral normalization. By constraining the discriminator's spectral norm, the largest singular value of each weight matrix, we cap its local Lipschitz constant. This prevents the discriminator from overreacting to small input perturbations, which in turn yields steadier gradients for the generator. The result resembles tuning a microphone with a built-in gain limit. The feedback you receive is informative but not wildly volatile. Spectral normalization often yields faster convergence and improved resilience to mode collapse across a family of DCGAN variants, particularly when combined with gradient penalties or other regularizers. When you pair it with a robust distance measure like Wasserstein, you get a discriminator that reports meaningful, bounded feedback even as training dynamics evolve. Third, the two-time scale update rule, TTUR. This principle codifies the intuition that the generator and discriminator should not learn at identical paces. Letting one network progress faster or slower helps maintain a healthy competition. The discriminator provides corrective signals without drowning the generator in noise, and the generator learns to exploit stable cues rather than chasing transient fluctuations. In practice, TTUR is implemented via asymmetric learning rates and update frequencies, often with the discriminator receiving more frequent updates in early stages. The synergy with Wasserstein loss and spectral normalization stabilizes the entire training loop and reduces mode-seeking instability. Beyond these three pillars, researchers evaluate progress with metrics like freshet inception distance to quantify realism and diversity, and often report precision recall analysis for GANs. Hybrid approaches combining VAEs with GANs or leveraging InfoGAN style auxiliary objectives further harness latent structuring to improve sample credit and controllability. In short, these advanced tools, applied judiciously, yield not only sharper imagery but more dependable training trajectories across diverse datasets. As training progresses across many iterations, the generator keeps refining its ability to hide flaws, but our feedback loop becomes sharper and more nuanced. Beyond simply looks realistic, we now care about stability and measurability. In practice, adding stabilization techniques such as spectral normalization in the discriminator to cap the Lipschitz constant and gradient penalties like WGAN-GP helps the model learn smoother, more reliable gradients. This reduces training oscillations and expressive yet faithful outputs. When we pair these stabilizers with thoughtful evaluation, we gain a clearer signal of progress beyond subjective judgments. Conditional DCGANs extend the idea of guidance with class labels, enabling targeted generation while mitigating mode collapse for long-tail categories. In addition to simple conditioning, we can employ discriminators that exploit class information through projection or auxiliary classifiers, which strengthens the alignment between label semantics and visual features. This is especially valuable in imbalanced datasets. The model can be steered to produce both abundant and rare categories, expanding the practical utility of the generator for tasks like dataset augmentation or controlled experimentation. Style-based GANs take control to a finer grain. The core idea, introducing a separate style vector that modulates features across multiple scales via a mapping network and adaptive instance normalization, lets us separate what an object is from how it looks. This enables semantic disentanglement that supports style transfer and robust exploration of appearance without sacrificing shape. In practice, style mixing experiments reveal a spectrum of plausible appearances for the same subject, and the style vector can be manipulated to adjust texture, color, or shape independently. For researchers, this means a more interpretable latent space and a richer set of experimental controls for both creative and scientific investigations. Cycle-consistent GANs address the challenge of unpaired data. By adding a cycle loss, the model learns a reliable two-way mapping translating from domain A to B and back again should recover the original image. This expectation encourages faithful translations even without paired examples, benefiting style transfer and domain adaptation. In setups where paired data are scarce, cycle consistency acts as a strong regularizer, improving fidelity and reducing reliance on large label corpora. To assess these advances, we rely on robust metrics such as FID and kernel-based alternatives like KID, alongside traditional inception scores. We also consider precision recall analysis for a fuller picture of diversity versus fidelity. Finally, hybrid approaches combining GANs with VAEs, InfoGAN-style disentanglement, or even diffusion model ideas hold promise for richer representations and more controllable generation. Together, these developments move DCGANs from curiosity-driven experiments toward deployable tools for design, science, and interactive media. To bridge from what you've just heard to what's coming, think of DCGANs as a friendly duel between two neural nets, a generator weaving new images and a discriminator judging their realism. That push and check loop not only produces convincing faces and artwork, but practical gains like data augmentation and rapid prototyping. In the next slides, you will see how these ideas extend to video, where patterns become short, believable clips and higher detail through super resolution. You'll also learn how anomaly detection teaches models what normal looks like. So unusual shapes in medical scans or defect patterns on a factory line stand out. We'll then explore three core use cases: medical image synthesis, game and VR content creation, and realistic simulations, and finish with a candid note on data quality, bias, and future improvements such as color fidelity and multimodal outputs. Beyond the familiar demonstrations of what DCGANs can generate, the current practice emphasizes how to train them more reliably, how to measure what they produce, and how to extend their capabilities in principled ways. I lay out these threads without revisiting the basics of the two-player game and instead focus on stability, evaluation, and hybrids that researchers often pursue in practice. First, stability and regularization. A central challenge with DCGANs is keeping training stable as the generator and discriminator chase each other toward better realism. Spectral normalization constrains the spectral norm of each layer in the discriminator, providing a controlled Lipschitz constant and reducing sensitivity to small input perturbations. This simple adjustment can markedly reduce training oscillations and mode collapse in practice. Another route is gradient penalties, popularized in Wasserstein GANs with gradient penalty WGAN GP. By penalizing deviations of the gradient norm from 1, the model enforces a smoother objective landscape, which helps when the standard Jensen-Shannon loss becomes problematic for optimization. In tandem with these, careful weight initialization, choice of activation functions e.g. leaky real U in the discriminator, real U in the generator with a tan output, and prudent learning rate scheduling contribute to more stable convergence and better sample quality. Second, architectural and training refinements. Transpose convolutions can introduce checkerboard artifacts. Many practitioners mitigate this by using upsampling, nearest neighbor, or bilinear, followed by convolution or by advanced upsampling strategies that reduce patterning artifacts. Hybrid regularizers and normalization schemes, such as omitting batch normalization in very deep discriminator stacks or adjusting it in the generator, can also influence stability and diversity of outputs. Hybrid or conditional variants, where auxiliary information guides, generation labels, attributes, or textual descriptions provide greater control and can improve both fidelity and interpretability of the synthesized content. Third, rigorous evaluation. Quantitative metrics matter for scholarly comparability. Frechet inception distance (FID) is now a standard for assessing both realism and diversity by comparing feature distributions of real and generated images in a pre-trained network's embedding space. Lower FID is better. The inception score offers a complementary perspective on confidence and variety, but has limitations when real-world diversity is broad. More granular diagnostics, such as precision recall curves for generative models, can reveal whether a model produces high-fidelity samples at the expense of coverage or vice versa. Complement these with human judgments and task-relevant benchmarks when possible. Finally, ethics and responsible use. As these models mature, the potential for misuse, such as synthetic but convincing phases, requires careful governance, consent-aware data practices, and transparent reporting of model capabilities and limitations. When deployed thoughtfully, DCGANs and their successors remain valuable catalysts for exploration, rapid prototyping, and creativity alongside rigorous evaluation. Today, we can expand on how DCGAN style video generation moves beyond crafting single frames to producing temporally coherent clips, and how modern advances help us train, evaluate, and deploy these models with greater rigor. First, consider training stability and realism at scale. The raw GAN objective can still struggle with oscillations and mode loss when extended to video. Two cornerstone techniques address this: spectral normalization and gradient penalties. Spectral normalization constrains the Lipschitz constant of the discriminator by rescaling weight matrices, which stabilizes learning from frame to frame and reduces sensitivity to bursty gradients across time. Gradient penalties, as popularized in WGN GP, enforce a soft Lipschitz constraint on the generator discriminator path, encouraging smoother transitions and more consistent temporal dynamics. Together, these tools help the model learn reliable spatiotemporal patterns, how shapes, textures, and motion evolve together without collapsing to repetitive or blurry clips. Second, advancing the architecture to capture motion precisely. Early DCGAN extensions used 3D convolutions or two-stream designs to model spatiotemporal structure, but we now see richer approaches. temporal discriminators that focus on motion consistency, motion-aware losses that penalize temporal artifacts, and attention or transformer-based modules that model long-range dependencies across frames. Hybrid designs pair a strong spatial generator with a temporal predictor or recurrent backbone, for example, con-LSTMs or gated attention over time, to maintain coherence over longer sequences. In practice, incorporating optical flow-inspired constraints or difference-based losses helps ensure that the generated motion aligns with plausible physical dynamics. Third, evaluation has become more discerning. Frame-wise metrics like PSNR or SSEM miss temporal quality. Freshet video distance (FVD) measures how close generated videos are to real ones in a learned feature space, while kernel inception distance KIT provides a distributional view with kernel methods. Perceptual quality also benefits from LPIPS-based assessments. When reporting results, we should pair FVD divided by KID with temporal coherence test and, where possible, task-driven evaluations, e.g., how well a model supports video prediction or downstream simulation. For super resolution, join metrics that combine fidelity and perceptual quality along with task-specific measures like downstream recognition, accuracy, or informative. Fourth, hybrid and alternative paradigms. Diffusion-based video generation is gaining traction for stability and controllability, often used in tandem with refinement stages to sharpen detail after a coarse DCGAN-like generation. Two-stage pipelines, low-resolution video synthesis, followed by super-resolution and detail enhancement often outperform single-pass models, especially when coupled with perceptual and temporal losses. Let me extend the slide's two big ideas by focusing on how we make these DCGAN-powered workflows robust, evaluable, and expandable in practice. You already know the three application domains, so I'll move beyond the basics to stabilization, evaluation, and hybrid strategies that researchers and practitioners are actively exploring. Medical image synthesis is a compelling case where realism, privacy, and data diversity must align. In addition to generating synthetic scans, we can strengthen training stability by applying spectral normalization to the networks. This constrains the Lipschitz constant of the critic and generator, reducing gradient instability and helping the model avoid sharp, unrealistic artifacts as the resolution increases. Gradient penalties, think WGANGP style terms that regulate gradient norms with respect to inputs, further promote smoother, more truthful mappings from latent space to image space. We can also leverage conditional DCGANs to target modalities, MRI versus CT, or pathologies, enabling controlled augmentation for rare cases. For evaluation, we should go beyond a single number, pair FID with domain-aware metrics such as SSIM and PSNR, and incorporate perceptual similarity measures like LPIPS. In practice, radiologist in the loop, scoring, or task-based assessments A.G. Diagnostic accuracy with and without synthetic data provide essential validation. Hybrid models are attractive here. A DCGAN backbone can be augmented with diffusion-based refinements or a VQ-VAE encoder to produce a structured latent space that preserves clinically relevant features while enabling high fidelity. This combination can deliver faster initial synthesis with a final pass that elevates detail and realism. In game content creation, stability matters at scale, textures, characters, and environments must be diverse yet coherent across views and lighting. Spectral normalization and gradient penalties stabilize large multi-view generators that produce, for example, branching textures or modular characters. Conditional or controllable DCGANs give designers a knob to steer style, mood, or armor type, while a hybrid GAN diffusion pipeline can offer crisp textures with consistent material properties. Evaluation blends objective metrics FID or LPIPS on domain-tailored asset sets and human studies with artists and players to gauge perceived quality and immersion. Procedural content benefits from explicit diversity metrics and coverage analysis to avoid mode collapse. Virtual reality and simulations demand consistent geometry, lighting, and motion cues across scenes. Here, stabilization techniques reduce artifacts that break presence. Multimodal conditioning color, depth, and lighting cues enables more believable environments. A hybrid approach might use a DCGAN for rapid scene roughing, followed by a diffusion-based stage to refine textures and lighting, ensuring photorealism without prohibitive compute. Finally, evaluation should combine quantitative measures, domain-adapted FID divided by LPIPS, SSIM for specific views, with immersive user assessments and task-based testing e.g. simulator fidelity in training scenarios. Across all three areas, the overarching goal is to balance speed, accuracy, and ethical use while embracing advanced stabilization, principled evaluation, and thoughtful hybrid designs to push DCGANs from curiosity to dependable, high-impact tooling. Before we dive deeper, it's worth noting that high-quality images with DCGANs aren't magic. At large sizes, details blur and textures feel off because the model must learn many pixels at once. As you scale resolution and model size, training becomes expensive, demanding powerful hardware and long runtimes factors that limit access for students and educators. Ethical questions also accompany capability. How to prevent misinformation, protect privacy, and be transparent about synthetic media. So next, we'll explore responsible uses and practical guidelines, design-forward applications with consent, ways to limit tool access, and clear marking of generated content. Then we'll examine why the models make certain choices, explainability, cross-domain generation challenges, and how reinforcement learning can help always with safety and trust in mind. Finally, we'll touch real-time, multimodal media and personalized content, underscoring why safeguards matter. First, the resolution challenge remains stubbornly architectural and optimization driven. At high pixel counts, the network must coordinate a staggering number of details, which often leads to unstable gradients, texture blur, and synthetic artifacts. Two advances help here. Spectral normalization constrains the discriminator's spectral norm, stabilizing adversarial feedback across layers and making training more predictable as you scale up resolution. Gradient penalties, as in WGAN GP, enforce a Lipschitz constraint that reduces sharp, unstable oscillations and helps mitigate mode collapse when you're learning with millions of pixels. You can also leverage progressive growing or multi-scale discriminators to guide detail synthesis gradually from coarse structure to fine textures so that the model learns coherent high-frequency content without overwhelming the optimizer. In practice, combining these with 2x scale updates, carefully tuned learning rates for generator and discriminator often yields more reliable convergence in high-resolution regimes. When evaluating, rely not only on traditional metrics but also perceptual ones to capture fidelity across scales. Second, cost and scalability remain central concerns. Training at high resolution and with large generators scales linearly with data and computational budgets, which can limit access for students and smaller labs. To address this, engineers use mixed precision training, model pruning or factorization, and distributed data parallelism to squeeze throughput without sacrificing quality. Hybrid modeling strategies are also promising. For example, integrating diffusion-like diffusion steps with GAN-style refinement or using VQVAEs as a compact, informative prior that a GAN then sharpens. These hybrids can deliver sharper details with fewer training iterations and better stability than a plain DC GAN at the same resolution. Third, ethics and governance must be embedded in the workflow. As synthetic imagery becomes more capable, misrepresentation risks grow. Practical safeguards include conspicuous generation markers, robust model cards describing capabilities and limits, access controls for high-risk tooling, and transparent provenance, so researchers and journalists can distinguish synthetic from authentic content. Encouraging verification workflows, education about source questioning, and privacy-respecting data practices helps ensure these technologies augment truth rather than undermine it. From a research perspective, the path forward combines stronger stabilization, spectral norm, gradient penalties, TTUR, smarter training curricula, progressive divided by multi-scale strategies, rigorous multi-metric evaluation, fit KID, LPIPS, precision divided by recall analysis, and thoughtful, ethical deployment. By balancing technical innovation with clear accountability, we can realize high-resolution synthesis that is both impressive and responsible. Now, I want to move beyond the intuition of more realism and talk about explainability in GANs as a practical research objective one that strengthens trust, safety, and deployment in real-world settings. Explainability here means more than describing outputs. It means understanding how and why certain images emerge from the generator and how the model's decisions relate to human understandable features. A productive path is to build explainability into design and training, not as an afterthought. We can favor architectures and regularizers that make the mapping from latent codes to visuals more interpretable. For example, spectral normalization constrains the Lipschitz constant of the network, yielding more stable gradient behavior. This stability helps us reason about which latent directions produce which perceptual changes, reducing black box wandering in the latent space. Complementarily, gradient penalties, like those used in WGAN GP or R1 divided by R2 penalties, smooth the loss landscape, dampening abrupt fluctuations that cloud causal interpretation. When the optimization landscape is smoother, we can diagnose failures more reliably. Is a misfire due to feature misalignment or due to a brittle region of the loss surface? Evaluation of explainability should accompany traditional quality metrics. Alongside freshet inception distance and kernel-based metrics, researchers are increasingly adopting precision divided by recall for generators to separate fidelity from diversity. But we also need explainability-focused checks, sensitivity analysis, ablation studies, and feature attribution exercises that reveal which inputs or latent directions drive specific image traits. In practice, this means pairing quantitative scores with qualitative human-centered interpretations e.g. asking what visual features correspond to certain latent access and how these features interplay with domain cues. Cross-domain generation remains a central challenge. Domain shift and feature inconsistency hinder transferability from, say, schematic drawings to photorealistic scenes. Advances in alignment techniques, adaptive normalization methods like Aiden, Spade, and cycle consistency refinements help align edges, colors, and textures across domains. Adaptive learning then plays a role. Mechanisms that adjust the model's rules as new domains arrive can preserve explainability by keeping the decision logic stable while expanding the feature space. Integrating reinforcement learning with GANs offers a promising route to guided explainability. Reward signals can incentivize not just realism but alignment with human preferences or safety constraints. However, balancing adversarial and reinforcement signals is delicate. Stability-focused loss terms and thoughtful training schedules are essential to maintain trustworthy behavior. Hybrid approaches also deserve attention. Combining GANs with diffusion priors or VAE components can render the generative process more transparent, enabling intermediate representations that are easier to inspect and explain. In the end, researchers are converging on three aims: transparent rationales for model decisions, cross-domain robustness, and learning that improves with more data without compromising interpretability. This trio is what will make GAN-based systems more trustworthy, flexible, and ultimately useful to researchers and practitioners alike. Real-time content generation with DCGANs is advancing toward on-demand media creation, but we are moving beyond basic demonstrations into systems that are robust enough for classroom and production environments. In this talk, I'll layer in some advanced ideas that help migrate from proof of concept to reliable real-time pipelines. First, stabilization and quality at speed. Classic DCGANs can struggle with sharp details and consistent colors under tight latency budgets. A practical approach is to bring spectral normalization into the discriminator. By bounding weight magnitudes, spectral normalization reduces the risk of exploding gradients and helps the network learn more stable, generalizable features. Combined with gradient penalties, what you often see in WGAN-GP, this enforces a softer Lipschitz constraint and promotes smoother gradient flow. The payoff is higher quality samples with fewer artifacts while maintaining faster convergence, a boon for time-constrained generation cycles. Second, robust evaluation in real time. Traditional metrics like FID and inception score are useful for offline comparisons, but real-time systems need metrics tied to timing and coherence. Freshet inception distance remains valuable for image quality, while Freshet video distance (FVD) extends this to temporal coherence across frames. In practice, you'll also track latency per frame, frames per second, and tail latency, ensuring the system meets hard deadlines. Perceptual metrics cosine similarity in learned feature spaces and task-oriented metrics like user-rated fluency help align automated scores with human judgments. Third, architectural and hybrid strategies. Pure DCGANs are fast at generation but can cap quality. Hybrid models can bridge speed and fidelity. For example, a fast DCGAN-based generator provides a coarse frame sequence followed by a lightweight refinement network, which could be another GAN or a small diffusion-like module that polishes details frame by frame or across a short temporal window. This two-stage approach can yield high-quality outputs with low overall latency. Progressive growing concepts, producing initial low-resolution frames quickly and refining them, can also help maintain responsiveness in real-time pipelines. Cross-modal and multimodal extension is another frontier. Multimodal synthesis text, images, and sounds requires tight cross-modal alignment. We can incorporate cross-modal encoders and joint embedding losses to improve consistency across modalities, using temporal alignment constraints and perceptual losses to preserve the intended mood or narrative. In practice, captions paired with visuals and synchronized soundtracks demand accurate timing models and coherence checks. Finally, personalization and ethics. Real-time, personalized media raises privacy and authenticity questions. On-device inference, strict consent and data minimization policies, and explicit watermarking or provenance tags help balance innovation with responsibility. Transparent guidelines and measurable safeguards, privacy by design, user controls, and auditable outputs build trust as these systems scale. In short, achieving real-time, high-quality DCGAN-based generation hinges on stable optimization, spectral norm, gradient penalties, robust multimodal evaluation, hybrid architectures that balance speed and refinement, and principled ethics and provenance. With these elements, we move closer to interactive museums, adaptive classrooms, and dynamic game environments that feel both responsive and believable. DCGANs showed that replacing dense layers with convolutional ones gave us a stable path from pixels to plausible images. The generator and the discriminator could reuse features, sharpening training and freeing the model to learn structure from real photo collections. That shift set the stage for clearer visuals and more reliable experimentation. But it isn't a perfect shortcut. Mode, collapse, and sensitivity to learning rates remind us that balance between the two networks matters. In the next sections, we'll pull apart the practical levers, batch size, normalization, architecture depth, and how they steer realism toward diversity. We'll summarize what DCGAN did well: stable training, quality output, a blueprint for successes. We'll also note the limits, and then look ahead to bigger questions: new architectures, smarter training, ethics, and the dream of real-time, adaptable generation. Let me frame this by looking at the downstream influence of DCGAN beyond its own construction. We won't revisit the basics. Instead, we'll trace how its design choices seeded stability, enabled higher fidelity, and shaped the research agenda that followed. This is where we see a shift from "can this work at all?" to "how far can we push reliable image synthesis?" She assured. First, the stability afforded by a convolution-driven backbone opened practical pathways for scaling. By constraining the flow of information through hierarchical, localized patterns, researchers could train deeper generators and discriminators without the training collapse that plagued earlier GANs. This stability is what made it feasible to train on real photo collections and to begin integrating more sophisticated regularization and normalization techniques. In parallel, researchers introduced mechanisms to control the network's functions more precisely. Spectral normalization, for example, became a standard tool to cap the discriminator's Lipschitz constant, helping to prevent sudden destabilizing gradient spikes. Gradient penalties popularized in WGAN-style objectives offered another robust route to smooth training dynamics. Collectively, these ideas built on DCGAN's stable core and gave us a principled way to reason about convergence, rather than relying on trial and error alone. Second, the impact on image quality and experimental reliability was tangible. The architecture encouraged sharper, more natural-looking outputs and more dependable training curves, which in turn lowered the barrier for systematic experimentation. This reliability made it easier to deploy and compare variants, to benchmark against evolving evaluation metrics, and to iterate toward higher fidelity. The fresh at inception distance emerged as a pivotal metric for quantifying how closely generated samples approximate real image distributions, complementing qualitative assessments and guiding architectural refinements. In practice, this meant that progress could be tracked with a more objective lens, accelerating the pace of improvement. Third, DCGAN provided a clear blueprint that influenced a swath of subsequent work and applications. It became a common reference point for generator discriminator design and for exploring how to stabilize training while preserving realism. However, the approach also revealed enduring weaknesses, most notably mode collapse and limited diversity. While the backbone remained strong, practitioners discovered that real-world variety required more explicit diversity maintenance, better hyperparameter guidance, and architecture-aware regularization. This awareness propelled hybrid approaches combining DCGAN-like blocks with VAEs or flow-based components, or integrating spectral norm and gradient penalties directly into GAN objectives. Key takeaways: DCGAN gave us a stable convolutional training regime and consistently high-quality outputs. It provided a reliable platform for experimentation and benchmarking. And it highlighted limitations in diversity that spurred a broad family of improvements from normalization and penalties to hybrid models and more nuanced evaluation. Building on the DCGAN foundation, I want to emphasize how the architectural shift to convolutional layers opened the door to deeper, more expressive, unsupervised models. The generator and discriminator no longer rely on dense connections that flatten spatial structure. The shared filters learn hierarchical, image-wide features that generalize across scales. This design makes it practical to stack many more layers without exploding parameters, which in turn yields sharper, more realistic images and more reliable generation across many atoms. Beyond architecture, stability became a central concern as we pushed depth and realism. A set of advanced regularization and normalization tricks help keep training under control. Spectral normalization constrains each layer's Lipschitz constant by normalizing the weight matrix spectral norm, which stabilizes the discriminator's updates and reduces sensitivity to large gradient swings. In parallel, gradient penalties, most famously used in WGAN GP, penalize deviations from a one Lipschitz constraint along interpolations between real and fake samples. These penalties often improve convergence when batch normalization interactions are tricky or when the datasets are challenging. When applying these ideas to DCGAN-like architectures, you typically see steadier training dynamics and fewer mode fluctuations. Evaluation has matured as well. In addition to visual inspection, we now rely on metrics that quantify both quality and diversity. The freshest inception distance, or FID, compares distributions of real and generated images in a deep feature space, usually inception features. Lower FID indicates that the generated distribution matches the real one more closely in both perceptual quality and variety. It's important to interpret FID alongside human judgments and other metrics because no single score perfectly captures perceptual realism. Hybrid and extended models give us even more control over representation learning. Adversarially learned encoders, as in ALI or BiGAN, couple an image encoder with a GAN, enabling meaningful latent representations and bidirectional mapping between latent codes and images. VAE-GAN hybrids blend variational objectives with adversarial feedback to improve reconstruction quality while preserving sharpness. These hybrids illustrate a broader paradigm. The latent space becomes not only a source of diversity but also a means to inspect and manipulate generated content. Finally, practical considerations matter. To mitigate checkerboard artifacts, researchers have moved toward upsampling, followed by convolution or subpixel convolutions rather than deconvolution alone. Tuning learning rates, batch sizes, and penalty weights remains essential. A cautious, staged approach, moderate initial learning rates, then gradual adjustments guided by sample quality and diversity helps maintain that healthy generator-discriminator balance. In short, DCGANs demonstrated how architectural choice, stabilized training, robust evaluation, and thoughtful hybrids collectively advance deep, unsupervised image synthesis. Thank you for taking the time to explore where generative models stand and where they might take us next. Models like DCGANs have opened exciting avenues for creative work, enabling designers to prototype visuals quickly, helping students stage ideas, and letting storytellers render vivid scenes that would be hard to conjure by hand. In classrooms, they can illuminate synthesis, interpolation, and conditional creation with tangible demonstrations. Yet these promises come with real challenges that we must address collaboratively. From a technical perspective, training remains only partially predictable in the early phases. Even when the end results look impressive, we worry about mode collapse, artifacts, and outputs that drift as the two networks chase one another. Diversity is still a hurdle. Outputs can appear strikingly similar across samples, limiting their usefulness for exploration and discovery. To push beyond these hurdles, the field has developed several stabilizing tools. Spectral normalization constrains the discriminator's spectral norm to temper its learning dynamics. Gradient penalties, such as those used in WGAN GP, enforce Lipschitz continuity to stabilize updates. Together, these approaches help create steadier training trajectories, reducing catastrophic forgetting and improving robustness. More generally, carefully designed loss landscapes and learning rate schedules, for example, 2 timescale updates, contribute to more reliable convergence and better generalization, even when data are imperfect or limited. Beyond stability, robust evaluation remains essential. We rely on metrics like freshet inception distance and its cousins CID, LPIPS to quantify realism and perceptual similarity, while precision and recall-like measures provide insight into diversity and distribution coverage. However, no single metric fully captures the nuanced notion of quality across looks, realism, and usefulness. Complementing quantitative scores with human judgments and task-specific benchmarks is still indispensable. Looking forward, hybrid models and architectural innovations blending discriminative guidance with diffusion-inspired dynamics or integrating GANs with VAEs and other objectives may offer richer representations and better sample efficiency. To accelerate progress, I encourage experimentation along a few practical lines. First, adjust architectural layouts to shape the output manifold. Second, explore alternative loss formulations and stability-enhancing penalties. Third, mix datasets to broaden prior knowledge and reduce overfitting. Fourth, incorporate conditioning to steer outputs toward desired themes. Fifth, test smaller models with practical training schedules to enable rapid iteration and deployment. Open questions remain vibrant. How to balance creativity with control in real-world tasks, how to measure multidimensional quality, how to reduce bias and ensure fair outputs, whether learning can be achieved with less data and compute, how to address privacy and ethics in training data and use, what architectures beyond DCGANs will push limits further, will real-time generation become routine for interactive applications, and how we can better interpret what the model has learned and why. The field is moving quickly, and every experiment teaches us something important. The future looks exciting. More capable tools to augment art, science, and education, approached with responsibility and thoughtful evaluation. Together, this deck has walked you through the role of references as more than decoration signposts that guide inquiry, anchor claims, and invite verification. By contrasting books and peer-reviewed articles with online material, we highlighted the criteria that make sources trustworthy: author credentials, publication date, and publisher, plus the absence of an author as a warning signal. The habit of consulting multiple sources, cross-checking facts, and aligning citations with your argument strengthens scholarly rigor and integrity. As you prepare submissions, let references serve not only as evidence but as a map of the research landscape, showing where ideas come from and how they evolved. The journey of learning is ongoing. Cultivate discernment, curiosity, and responsibility as you engage with sources in future work. Today, we revisit the DCGAN story not as a retrospective of a single paper, but as a map of how its blueprint galvanized a broader research program. DCGAN gave us a surprisingly sturdy, scalable blueprint for unsupervised image generation. A deep convolutional generator and discriminator trained in tandem with a clear set of architectural decisions that made training more reliable and results more interpretable. By moving away from pooling using upsampling inside the network and incorporating deconvolutions or fractional convolutions to grow image size, the authors demonstrated that learning stable, high-quality image representations was not merely possible but practical at meaningful scales. Batch normalization in both networks with ReLU in the generator than on the output and leaky ReLU in the discriminator created a reproducible path to sharper features and more consistent convergence. The upshot was not only better-looking images but also a compelling argument for unsupervised learning as a path to rich feature representations. Since then, the DCGAN blueprint has become a springboard for more advanced stability tricks and robust evaluation. A central thread has been Lipschitz control of the discriminator. Spectral normalization, popularized to bound the spectral norm of weight matrices, provides a simple, effective way to stabilize training across architectures and datasets, and it has been adopted in DCGAN-style models to keep the discriminator's gradients well-behaved without crippling capacity. Another influential thread is gradient penalties, notably the WGAN-GP approach, which enforces a soft Lipschitz constraint by penalizing the gradient norm on interpolations between real and fake samples. Together, these ideas reduce sensitivity to hyperparameters and batch statistics, helping researchers train at higher resolutions and broader data regimes. Evaluation metrics have also matured. Frechet inception distance became a standard for comparing real and generated distributions in a shared feature space, balancing sample quality and diversity in a single score. It complements, and in some contexts, supersedes older metrics like inception score. Practically, FID has become the benchmark used to assess progress across datasets from CIFAR to LSUN, guiding iterative improvements. Architectural and methodological hybrids have emerged from the DCGAN lineage. Progressive growing, ProGAN, and style-based approaches, StyleGAN, extend the DCGAN spirit by addressing stability and fidelity at ultra-high resolutions, while VAE GAN and BiGAN divided by ALI hybrids fuse encoder-decoder ideas with adversarial training to endow generative models with inferential capabilities. These hybrids highlight a core theme. The most impactful advances often blend architectural insight with principled regularization and robust evaluation. In short, DCGAN's impact is enduring because its design choices offered a clear, workable recipe, and what followed shows how researchers refined that recipe with spectral norms, gradient penalties, rigorous metrics, and thoughtful hybrids to push the boundaries of what unsupervised generation can achieve. Moving from the basics of GANs to productive, research-oriented learning means choosing materials that tie theory to rigorous practice and credible evaluation. Textbooks remain a solid backbone. They typically provide the full stack, how generators and discriminators interface, why convolutional layers matter for image synthesis, and how architectural choices map to learning dynamics. As you read, look for chapters that go beyond recipes to address stability, convergence, and the role of regularization. In particular, seek discussion of modern stability techniques, spectral normalization to constrain the discriminator's Lipschitz constant, gradient penalties such as WGAN GP to enforce smoother landscapes, and the TTUR 2-timescale update rule for coordinated generator discriminator training. These topics help you understand why certain DCGAN and related architectures behave more robustly in practice, and they provide mathematical intuition you can test in your own experiments. Online courses and tutorials are where theory meets hands-on coding. They typically guide you through building and diagnosing GANs end-to-end, but the best offerings also introduce contemporary improvements and evaluation practices. When you engage with these courses, look for modules that implement not just vanilla DCGANs, but also enhancements like spectral normalization and gradient penalties, progressive growing, or style-based generators. Honest evaluation training matters here. You'll encounter metrics such as freshet inception distance and its relatives, kernel inception distance, KD, as well as precision divided by recall metrics for generative models. Some courses integrate perceptual or feature matching losses and discuss how to balance realism with diversity. Hybrid models combining GAN objectives with reconstruction or latent code-driven objectives, e.g. VAE, GAN, InfoGAN, or encoder-decoder frameworks are a recurrent theme in advanced curricula, offering practical routes to controllability and interpretability. Open source implementations are more than just ready-made code. They are living laboratories that let us push DCGANs beyond the basics and into rigorous, repeatable research. In practice, the best repositories you'll find are not only well documented but actively maintained, with a community that curates architectural variants, training strategies, and robust evaluation protocols. You can study how researchers tweak layers, filters, and normalization schemes by reading the code, and you can reproduce published results to establish solid baselines before you experiment. A few advanced threads you'll notice across top repos relate to training stability and realism. Spectral normalization is a common feature in discriminators, constraining the Lipschitz constant of each layer to stabilize GAN training without compromising expressivity. You'll also see gradient penalties, such as those used in WGAN GP, integrated into the loss function to enforce smooth, meaningful gradients and mitigate mode collapse. Some projects experiment with hinge losses or other alternative objectives, comparing convergence behavior and sample quality. You'll also encounter TTUR, different learning rates or update frequencies for the generator and discriminator to balance their learning dynamics. These tricks are often modular in open source code, making it straightforward to isolate their impact. Evaluation metrics are essential in these repositories. In practice, you'll see FID, the Frechet inception distance, used to quantify how close the generated distribution is to real data in a learned feature space. Some projects pair FID with inception score, MS-SSIM for diversity, and precision divided by recall measures to assess both realism and coverage of the data distribution. These metrics, when used together, help you avoid the common pitfall of optimizing for a single statistic at the expense of other quality aspects. Hybrid and extended architectures frequently surface in open source work. Variants like VAE-GAN hybrids fuse encoding decoding with adversarial objectives to obtain more structured latent spaces, enabling bidirectional mapping and easier latent interpolation. Others explore progressive growing, style-based modulations, or encoder-free hybrids that blend GANs with energy-based ideas. Even within the DCGAN family, it's common to see modular components that researchers replace or augment, advancing from plain convolutions to normalized layers, residual connections, or attention mechanisms while preserving a familiar training loop. When selecting a repository, prioritize activity, clear documentation, and reproducible experiments, seed values, dataset splits, and evaluation scripts. Start by reproducing a published result, then perform controlled ablations, alter data quantity, learning rates, normalization schemes, or penalty terms, and measure changes with FID and related metrics. The open source ecosystem thus lowers the entry barrier to rigorous experimentation and invites collaborative refinement. In short, open source repos empower you to explore, audit, and share nuanced findings, transforming isolated experiments into a community-driven, evidence-based practice. Deep Convolutional Generative Adversarial Networks, or DCGANs, represent one of the earliest and most influential breakthroughs in generative AI. The DCGAN IPYNB notebook captures how these models take random noise and progressively transform it into realistic images, demonstrating the creative potential of adversarial training. At the center of the model are two neural networks locked in constant opposition: the generator, tasked with producing images, and the discriminator, trained to distinguish real from fake. Their interplay drives the generator to refine its outputs until they become indistinguishable from genuine data. What begins as meaningless noise evolves into structured visuals, an outcome that illustrates both the elegance and the challenge of this approach. The power of DCGANs lies in their architecture. By leveraging deep convolutional layers, they are able to capture spatial hierarchies in data, producing results far richer than earlier generative models. Yet the process is fragile. Training often risks instability, mode collapse, or failure to converge. The notebook showcases how careful tuning of losses, learning rates, and network design enables these systems to gradually stabilize and deliver convincing results. What emerges is more than a technical achievement. DCGANs mark the moment when generative AI first showed its ability to create images that could genuinely fool the eye. They laid the groundwork for many of the models that followed CycleGAN, StyleGAN, and beyond, demonstrating how deep learning could move beyond recognition and classification into the realm of creation. This notebook is not just an experiment in coding, it is a practical window into the mechanics of how machines learn to generate. By working through it, you see the progression from random noise to coherent visuals and gain insight into both the limitations and the potential of adversarial systems. In this section, the code is focused on setting up the necessary tools to generate animated GIFs. First, it installs the Imagio library, which is a versatile tool for reading and writing a wide range of image formats, including GIFs. This library will allow us to compile a sequence of images into an animated GIF later on. Next, it installs a package directly from GitHub, specifically from the TensorFlow documentation repository. This package likely contains additional utilities or code snippets that can assist with visualization or animation tasks related to deep learning models. By executing these installation commands, the notebook ensures that all the required dependencies are in place for creating visual animations, which can be particularly useful for illustrating the evolution of generated images during training or for showcasing the results of the GAN. This section begins with importing several essential libraries required for building and visualizing a deep learning model. We start by bringing in Globe, which is useful for pattern matching in file paths, helping us load image datasets efficiently. Next, Imagio is imported to handle reading and writing image files, which will be useful for saving generated images during training. Matplotlib PyPlot is included for creating visualizations, allowing us to plot images and monitor the progress of our generative adversarial network. The NumPy library is brought in for numerical operations, especially for manipulating arrays and image data. The OS module helps manage file paths and directories, ensuring our data and outputs are organized properly. PIL, the Python imaging library, provides additional image processing capabilities which can be useful for pre-processing or augmenting images. From TensorFlow's Keras API, we import the layers module essential for defining the neural network architecture, particularly the generator and discriminator models in our GAN. The time library is included to measure training durations or to create time-stamped outputs. Finally, the display module from IPython is imported to facilitate real-time updates in notebooks, such as displaying generated images dynamically during training. Altogether, these libraries set the foundation for building, training, and visualizing a deep learning model for image generation. In this segment of the code, we start by reshaping the training images to ensure they have the correct dimensions for our neural network. Specifically, we take the original array of images and reshape it so that each image has a height and width of 28 pixels, and we add an extra dimension for the single color channel since these are grayscale images. This results in a shape of number of images, 28, 28, 1. Next, we convert the data type of these images to floating point numbers to prepare for normalization. The normalization process then scales the pixel values from their original range, which is typically from 0 to 255, into a new range between -1 and 1. This is achieved by first subtracting 127, 5 from each pixel value, and then dividing the result by 127. Ooh. Normalizing the images in this way helps improve the stability and performance of the training process, especially when working with models like GANs that are sensitive to the scale of input data. In this part of the code, we set some fundamental parameters for our training process. We define a buffer size of 60,000, which is typically used for shuffling the dataset to ensure a good mix of data during training. This helps in preventing the model from learning any order-based biases. Additionally, we specify a batch size of 256, indicating that during each training step, the model will process 256 samples at a time. This batch size strikes a balance between computational efficiency and stable gradient estimates, enabling effective training for our deep convolutional generative adversarial network. We start by creating a dataset object from our training images using TensorFlow's data API. The from tensor slices method takes the array of training images and converts it into a dataset that can be processed efficiently. To improve training performance and ensure the model doesn't see the data in the same order every epoch, we shuffle the dataset with a specified buffer size. This shuffling helps to randomize the order of images, which is crucial for training stability. Finally, we batch the dataset into smaller groups of images, defined by the batch size, so that the model can process multiple images simultaneously during each training step. This code defines a function called makeGeneratorModel, which constructs the generator part of a deep convolutional generative adversarial network, or DCGAN. The generator is built using a sequential model where layers are added one after the other to progressively transform a random noise vector into a realistic-looking image. It begins with a dense layer that takes a 100-dimensional noise vector as input and produces a large, flat output of size 7 times 7 times 256. This output is then normalized via batch normalization, which helps stabilize training and pass through a leaky ReLU activation function to introduce nonlinearity. Next, the flat vector is reshaped into a 7x7 feature map with 256 channels, setting the stage for convolutional upsampling. The code includes an assertion to verify that the output shape is as expected, with the batch size left unspecified. Following this, a transposed convolutional layer is applied to increase the spatial dimensions. This layer uses 128 filters of size 5x5 with a stride of 1, preserving the 7x7 size but reducing the number of channels to 128. Again, batch normalization and leaky ReLU are used to improve training stability and introduce nonlinearity. The next layer is another transposed convolution, this time with 64 filters, a 5x5 kernel, and a stride of 2, effectively doubling the spatial dimensions from 7x7 to 14x14 while reducing the number of channels to 64. Batch normalization and leaky ReLU follow once more. Finally, the last transposed convolution layer upsamples the feature map to 28 by 28 pixels, matching the size of typical grayscale images like those in MNIST. It uses a single filter of size 5x5 with a stride of 2 and applies a tan activation function to output pixel values scaled between -1 and 1, which is common in GANs to match the data normalization. The function concludes by returning this constructed generator model ready to be trained to produce realistic images from random noise. We start by creating an instance of the generator model using the predefined function. Next, we generate a random noise vector which serves as the input to the generator. This vector is sampled from a normal distribution with 100 dimensions. And here we are creating a batch of 1. Passing this noise through the generator model with training set to false to indicate inference mode produces a synthetic image. Finally, we visualize this generated image using a grayscale color map displaying the first image in the batch. This process allows us to see the kind of images the generator creates from random noise inputs. This code defines a function called makeDiscriminator model, which constructs a neural network model used as a discriminator in a generative adversarial network. The model is built using TensorFlow's Keras API with a sequential architecture. It begins with a 2D convolution layer that applies 64 filters of size 5 by 5 with a stride of 2 and padding set to same to preserve spatial dimensions. This layer takes input images of size 28 by 28 with a single color channel. Following this, a leaky RealU activation function introduces nonlinearity, allowing small gradients when inputs are negative, which helps prevent issues like dying neurons. A dropout layer with rate of 0. 3 is then added to reduce overfitting by randomly disabling 30% of the neurons during training. Next, the model includes another convolutional layer with 128 filters, also of size 5 by 5 and with stride 2, again with same padding. This is followed by another leaky RealU activation and a dropout layer similar to the previous ones. After these convolutional layers, the feature maps are flattened into a single vector, preparing the data for the final classification layer. The last layer is a dense layer with a single neuron, which outputs a real valued score indicating whether the input image is real or generated. The function concludes by returning this constructed model ready to be compiled and trained as part of the GAN framework. In this section, we first create an instance of the discriminator model by calling the function makeDiscriminator mod. First, this model is designed to evaluate images and determine whether they are real or generated. Next, we pass a generated image stored in the variable generated image through the discriminator by calling it as a function. This produces a decision value which indicates the discriminator's assessment of the authenticity of the image. Finally, we print out this decision, allowing us to see the discriminator's output for the generated image. This line of code defines a helper function for computing the cross-entropy loss, which is a common loss function used in binary classification problems. Specifically, it creates an instance of TensorFlow's binary cross-entropy loss class with the parameter from logits equals true. This indicates that the inputs to this loss function are raw, unscaled logits rather than probabilities, which is typical in many deep learning models to improve numerical stability. By setting this up, the code prepares a straightforward way to evaluate how well the model's predictions match the actual labels during training, particularly in the context of a generative adversarial network where binary classification plays a key role. This code defines a function called discriminator loss, which calculates the loss for the discriminator in a generative adversarial network. The function takes two inputs, real output, which is the discriminator's output when processing real images, and fake output, which is the output when processing generated or fake images. Within the function, the first step is to compute the loss for the real images by comparing the discriminator's output to an array of ones, indicating that these images are indeed real. This is achieved using a cross-entropy function, which measures how well the discriminator is identifying real images correctly. Next, it calculates the loss for the fake images by comparing the discriminator's output to an array of zeros, since these images are fake. Again, the cross-entropy function quantifies how well the discriminator is identifying the generated images as fake. Finally, the total loss is obtained by summing the real and fake losses, providing a comprehensive measure of how well the discriminator is performing in distinguishing real from fake images. This total loss is then returned, guiding the training process to improve the discriminator's accuracy. This code defines a function called .generator loss, which calculates the loss for the generator in a generative adversarial network. It takes as input the discriminator's output on the fake images produced by the generator, referred to here as fake output. The goal of the generator is to produce images that the discriminator classifies as real. So the loss function compares the discriminator's predictions on these fake images to an array of ones indicating real images. The cross entropy function computes the difference between these two, effectively measuring how well the generator is fooling the discriminator. If the discriminator confidently identifies fake images as fake, the loss will be higher, prompting the generator to improve its outputs. Conversely, as the generator improves, this loss should decrease, guiding the training process towards generating more realistic images. We begin by setting up the optimizers for both the generator and the discriminator networks. In this case, we are using the Adam optimizer for each, with a learning rate of 0, ling E. This choice helps ensure stable training by adjusting the learning rate adaptively. By defining separate optimizers for the generator and discriminator, we can fine-tune their training processes independently, which is essential for the delicate balance needed in training a generative adversarial network. In this section, we set up the directory and prefix for saving our training checkpoints. The variable checkpoint dir specifies the folder where all checkpoint files will be stored, in this case, a folder named training checkpoints. Next, we create a checkpoint prefix by joining this directory path with a file name prefix ckpt, which will be used as the base name for our checkpoint files. Then we instantiate a tf train checkpoint object, which is essential for saving and restoring the state of our training process. This checkpoint object is configured to track the optimizers for both the generator and discriminator, as well as the models themselves. By including the generator optimizer, discriminator optimizer, generator, and discriminator in this checkpoint, we ensure that all necessary components are saved, enabling us to pause and resume training seamlessly without losing progress. In this section of the notebook, we start by setting some key variables for our training process. We define the number of epochs to be 1, indicating that we will run through the dataset just a single time for now. Next, we specify the dimension of the noise vector, which is 100. This noise will serve as the input to our generator network to produce synthetic images. We also set the number of examples to generate during each visualization to 16, providing a manageable number of images to observe the progress of our generator. To facilitate consistent visualization, we create a seed, a fixed random noise tensor using TensorFlow's random normal distribution. This seed will be reused throughout the training process, allowing us to generate the same set of images at different stages. By doing so, we can clearly see how the generator improves over time, making it easier to track its learning progress. This seed acts as a reference point, helping us compare the generated images across different epochs and visualize the evolution of our model's capabilities. Training process by defining a function called thatTrainStep, which is decorated with @tf function, an optimized graph for faster execution. Inside this function, we start by generating a batch of random noise vectors each. Next, we utilize two gradient tapes, one for the generator and one for the discriminator, to record the operations for automatic differentiation from the noise, and both the real images and generated images are passed through the discriminator to produce their respective outputs. We then compute and the discriminator loss based on its ability to distinguish real from fake images. After calculating these losses, we obtain variables using the gradient tapes. Finally, we apply these gradients to update the parameters of both models via their respective optimizers. Setup ensures that both the generator and discriminator are trained simultaneously in a tightly integrated manner, improving the. This code defines a function called train, which is responsible for training a. Begins by looping through each epoch, recording the start time to measure how long each epoch takes. Within each epoch, it iterates over update the model based on each batch. After processing all batches in an epoch, it clears the previous output to keep the a helper function. This provides a visual progress update of the generator's outputs as training progresses. Every 15 epochs, that progress isn't lost and allowing for potential resumption later. Finally, once all epochs are completed, it clears train generator's results. Throughout, the code provides timing information for each epoch, giving insight into the training duration and preserving model states at regular intervals. Save images that takes in a trained model, the current epoch number, and a set of test inputs with the training parameter explicitly set to false to ensure the model operates in inference mode, which is especially in training and testing. Next, the code creates a new figure with a specified size of 4 by 4 inches. It then loops over each of creates a subplot arranged in a 4x4 grid, adds the image to the subplot, and adjusts the pixel values from the range -1, 7, 5 and adding 127. Ooh. The images are displayed in grayscale using the axmap. After all images are plotted, the figure is saved to a PNG file with a file name that includes the current epoch number, formatted to 4 digits for consistency. Finally, the image is displayed inline, allowing you to visually assess the quality of generated images at this particular training epoch. This function, named displayImage, is designed to open and display a specific image file corresponding to a given epoch number during the training process. It takes an argument called epoch no, which represents the epoch count, and formats this number into a file name that follows a consistent naming convention, such as image at epoch 1 png dash using Python's PAL image open method. It loads the image from disk and returns the image object. This setup allows us to easily visualize the progress of the generative model at various stages of training by simply calling this function with the desired epoch number. This code creates an animated GIF by combining a series of images. It begins by specifying the file name for the output GIF, which is named DCGAN. Then it opens a writer object using the Imagio library, configured to write an animated image. Inside this context, it searches for all files matching the pattern image asterisk PNG BLI, which are presumably a sequence of images generated during training or visualization. These file names are then sorted to ensure the images are ordered correctly in the animation. The code loops through each file name, reads the image data, and appends it to the GIF. After processing all images, it reads the last image again and appends it once more, likely to hold the final frame for a moment in the animation, giving viewers a clear view of the final generated image. Once the loop completes, the GA file contains a smooth animation that showcases the progression or evolution captured in the series of images. This notebook demonstrates how a generator and discriminator, locked in constant competition, can evolve from producing meaningless noise to generating images that feel real. What begins as unstable and uncertain gradually stabilizes through iteration, tuning, and persistence, showing how adversarial training drives both networks to refine their abilities. The process here goes beyond code. It illustrates a form of digital creativity, where neural networks not only learn to replicate patterns but also produce outputs that can surprise and inspire. Each experiment, whether adjusting hyperparameters, watching training curves, or troubleshooting instability, underscores how progress in this field is achieved through patience, curiosity, and iteration. The results serve as both validation and inspiration. They confirm that DCGANs can capture the essence of a dataset while also hinting at broader possibilities, faces that look human, landscapes that never existed, or artistic styles that blend the familiar with the novel. This notebook provides a foundation for those directions, a practical entry point into the world of generative modeling. As you move forward, I've already shared the code for this notebook in Teams. Please execute it on your end and let me know if you run into any issues. I'll be happy to guide you through.